Roger, cosmologists today are focused on how the universe began, focusing on inflation theory and various other things. But there's a more fundamental question. Did the universe begin? Because in the past, people assumed that the universe was forever and had different kinds of cycles or steady state or whatever. You've been a little bit of a renegade in terms of the traditional, now conventional wisdom of inflation theory beginning the universe. How so?
Well, one of the biggest motivations of the scheme, which I've been putting forward, for about 8 years now, let me just describe roughly the scheme. The current view is that the universe began with what's called the Big Bang. Immediately following that was a stage of inflation, which was an exponential expansion, which settled down, for one reason or another, into a more sedate expansion, which then became an exponential expansion, which is what we see, what got the Nobel Prize a few years ago, the accelerated expansion of the universe, which I regard as a consequence of the lambda term that Einstein introduced in his paper in 1917 for admittedly the wrong reason. He wanted a static universe just at the wrong moment when it was about to be announced that the universe was expanding. So he regarded that as his greatest mistake. In fact, it turns out that it wasn't a mistake, but not for the reason that Einstein originally introduced it. But there seems to be this exponential expansion, self-similar expansion, if you like. The rate of expansion depends on the state of the size of the universe. Now, this observed exponential expansion is what we expect to happen in our remote future, unless something else happens. And I believe it will extend into the remote future. Now, in inflation theory, there was a similar expansion in the very, very early stages after the Big Bang. Now, I've never liked inflation right from the start for various reasons. And I'm proposing a different idea, which is that, yes, there was inflation in a sense, but this was before the Big Bang. Now, an idea like that actually was put forward by the well-known, distinguished particle physicist Gabriele Veneziano, and he had a scheme in which the inflationary phase took place before the Big Bang, but that was sort of a one-off. The view I'm taking is that what we regard as the current picture of the universe, but without inflation, without the inflation immediately following the Big Bang, expansion and then the accelerated expansion, is just one eon. I'm calling it an eon, A-E-O-N, which is one of a succession of such eons. So there will be another after ours, there was one before ours, and the exponential expansion of that previous eon in its remote future is what appears to be inflation in our model. So there is in a sense inflation in this scheme, but it's not the kind of inflation that's argued for in normal physics.
Just order of magnitude, how long would an eon be? 10 to the what number of years?
A good order of magnitude is infinity.
Okay.
Because the view, you say, how can it be infinity?
Yeah.
Well, it depends on how you measure time, you see. This is an issue. And the argument is that to build a clock properly, you need mass. Now, we have incredibly precise clocks now. I don't know what the present record is, but if you think of all the time from the Big Bang to now, clocks are so precise that it's, well, at least something like only a few percent off it would be, to a few percent of a second off.
Yeah,
so measuring the time from the Big Bang, look, it doesn't mean we know the time from the Big Bang that accurately, but the clocks would keep time to that precision. Now, of course, they wouldn't survive in the Big Bang, but don't worry about that. Now, this precision in clocks, although it depends on a lot of technology and so on, ultimately comes from the fact that we have mass. Now, we have mass in the universe, and ultimately it is just the two most basic equations of 20th century physics. Of course, Einstein's E equals mc squared. C is just a constant, so E and m, energy and mass, are equivalent. The other great equation of 20th century physics is Max Planck's E equals h nu, well, F or whatever you call it, frequency. This tells you that energy and frequency are equivalent. So putting these two equations together, we conclude that mass and frequency are equivalent. So any stable particle is a clock in a sense, with a very, very precisely defined frequency. Now, other way around is that if we didn't have mass, we don't have clocks. And if you don't have clocks, you don't have a measure of time, you don't have a measure of distance. In fact, the meter rule, you see, in Paris is no use anymore. You would have to...
Start at that size.
Yes. The meter rule in Paris is not a good definition of a meter anymore. You define meter in terms of how long it would take light to travel.
Yeah.
Whatever fraction of a light second it is, and so on. So it's really time that is the thing that defines the scale of things. Right. Now, that scale requires mass in one way or another. Either the mass defined by particles, or in general relativity, we have another good measure of clocks from neutron stars going around each other. And again, just about as accurate. You have another measure of time, but that requires general relativity, and general relativity is a theory of gravity, and gravity requires mass. So those are things which involve mass in one way or another. If you didn't have mass, scale is irrelevant. Big and small are equivalent. So the idea is, well, on the one hand, when you go right back towards the Big Bang, energies get so great that the masses of particles become irrelevant way earlier than the Higgs particle time, if you like. Then the particles become effectively without mass, they're massless. And so they don't have a way of measuring the scale. Going to the remote future, almost all the particles around will be photons. Photons, again, don't have a good measure of time. So they don't know big from small. So the idea is that the very remote future, and when I say very, I really mean right out to infinity, is like a Big Bang. Now that's a big, difficult thing to get your mind around, because we think of one as stretched out and very...
And the other is...
The other is very squashed and very dense and hot. Right. The other is very cold. And all.
Right.
But when you squash the cold thing very undense together, you get something very like the Big Bang. So the argument is that the very remote future of what I'm called the eon, prior to ours, what I'm postulating that existed, prior to ours, that infinity was our Big Bang. You need equations to make sense of it, but that you can do. And that carries you through from the physics, which was the very remote future of the previous eon, to tell us what our Big Bang should be like.
And just walk me through that transition one more time, where you have the previous eon being expansion into where there's effectively no mass.
Yes.
So you can't tell the difference if it's big or small at that point.
That's right.
And then what's that transition to generate the Big Bang?
Well, and people always ask me this. You say, when did it happen? Well, you see, infinity is a perfectly good place in this scheme.
Right.
But you really need the equations. And it makes a lot of sense when you start. You just put down the transformations, which make infinity squash down, and then you take the reciprocal, and that's the stretching out, which gives you for the Big Bang. And okay, you've got to have some other equations to make this unique. So there's a bit of delicate problems.
And if we would go with that, which is a big step, but if you go that, then you could have that infinite in both directions. You don't have to have a beginning. You just could have these endless aeon cycles, however long they are. Well,
the beginning is at a definite time because
of each one.
Yes, of each one. That's right.
Yeah, but there's no beginning to the whole sequence.
There's no big. That's right. Yes. No, it's you could imagine a model where they change or something, but that's not what I'm putting forward. The idea is, yes, the previous eon was in general terms like ours. The one before it was in general terms like ours, and so on, indefinitely. In both directions.
And when you stop and think about it, the question comes up, why is reality like that?
Questions of this sort, I don't think I can go very far towards answering. But I don't know why reality, I don't know what is reality or why reality is what it is. I mean, in the scheme, it's a bit like the old steady state model, you see, and I think I was to some extent influenced by that, because when I got interested in cosmology first at Cambridge, that was a time when Bondi and Gold and Hoyle were producing this theory, and my good friend Dennis Sharma, and they were all terribly excited about this idea of a universe that was always there, you see, and so I think that rubbed off on me to some degree. I was worried by how it didn't seem to make consistent sense with general relativity, and I think Bondi was worried by that too. And when people decided, yes, there was a Big Bang, and the evidence for that is pretty convincing, and so I went along with that. But nevertheless, there's something philosophically about the old steady state model. And it's interesting, you see, Einstein wanted a static model. Newton, in a similar way, wanted something unchanging forever like this. So there's something in us all, perhaps, which would like an eternal universe. And so it has an appeal of that kind. That's not a very scientific argument. But,
no, it's a legitimate one.
But I think perhaps a legitimate argument, because you might ask, why was the Big Bang exactly as it was? And it seemed to have lots of structure to it of various different kinds, you see. And why was that structure there? Well, if there was nothing before it, it's hard to answer that question. But here we say, yes, it had that structure at that Big Bang because the eon before it had the structure it had. Of course, it's an endless chain which goes on forever, but nevertheless, you can sort of, at each stage, answer that question.